Hello. Let's talk about centripetal force. So when an object is moving in a circle, its path is changing constantly, which means that you need a force in order to keep that object in the circular path. Centripetal force is the force that attracts an object to the center of its path. When I have an object moving in a circular path, the direction of the force is towards the center of the circle. That's important. So let's take a look at an example of how this works. In this case, I've got some approximate numbers. The moon takes about 28 days to orbit the Earth and has an orbital radius of about 400,000 kilometers. What's the orbital velocity of the moon? The first thing is the orbital velocity here is asking for my circular velocity of the moon. How fast is the moon actually moving? Well, let's take a look. So in this case, the period is 28 days. The radius is 400,000 kilometers, and I'm looking for my circular velocity. So my formula for that is 2 pi r divided by t, or divided by the period. All right, plugging things in, I've got 2 times pi times 400,000 divided by 28 days. Okay, this gets me a circular velocity of 89,759.79 kilometers per day. Now, notice this here is not a conventional unit for velocity, but this is still acceptable velocity units. So a velocity unit just has to be a distance unit divided by a time unit. So in this case, we have kilometers per day, which is a correct velocity unit. That is great. It's not a conventional one because normally we look at kilometers per hour or meters per second or all that sort of stuff. And I'm going to figure this out and see what this will be in a more conventional unit. But right now, that's the answer to the first part. Now, the second part here, in order to figure out the second part, it says, determine the force between the Earth and the moon. So this is my centripetal force because it's keeping the moon in orbit. If I draw this out here, what I've got is I've got the Earth like this, and I've got the moon over here, and the moon is going around the Earth in a circle or in an ellipse. It's close to a circle. What's happening is there needs to be a force pulling the moon towards the Earth. So whenever I have an object moving in a circular path, the force is towards the center of the circle. This is actually worth drawing out again. If I just draw a circle, yep, that's a perfect circle. I'm claiming it's a perfect circle. If there's the center of the circle, so say I've got a ball going like this. So let's say the ball is moving up in this case, so my velocity is in that direction. The ball's going counterclockwise. The force is this direction, and my acceleration is also towards the center of the circle. So one of the interesting things is that my velocity is perpendicular to my force and my acceleration. Remember that upside down T means perpendicular or 90 degrees? Velocity is perpendicular to the force and the acceleration in circular motion. That's important. So let's go here. I've got a moon and an Earth, and I'm trying to find the force. If I look for the force formula, my force formula is mass times v, or the circular velocity squared divided by the radius. There we go. mvc squared over r. Couple of things. I don't have the mass here. I actually should have put that in the question. So my mass is 7.37 times 10 to the 22 kilograms. Yep. And my velocity I have here, but I need to find that in meters per second. Otherwise, this is going to give me weird units for force. So I'm going to convert this here. If I go 89,759.79 divided by 24, this is kilometers per day. There's 24 hours in a day. So working that out gets me to 3,739.99 kilometers per hour. And then I could take that, divide it by 3.6, which works out to 1038.89 meters per second. So the moon is traveling just a little bit faster than a kilometer per second going around the Earth. That's pretty quick. All right, plugging these things in, my force is 7.37 times 10 to the 22 times 1038.89 squared divided by 400,000 kilometers, but I need this to be in meters. So notice here that my radius must be in meters in this case. Otherwise, my force units are going to be weird, because if I want newtons, I need to have meters and meters per second and kilograms here. So my radius must be in meters. Plugging all of this stuff in and figuring it out, my centripetal force works out to 1.99 times 10 to the 20 newtons. And there we go. That is an awful lot of force, but the moon is awful big. Keeping it in orbit around the Earth requires a large amount of force. So, a couple things here. Again, remember my velocity must be in meters per second. So you may need to do some unit conversions there to convert from velocity in this case, kilometers per day to kilometers per hour to meters per second. You got to do a little bit of conversions there, but that is totally doable. And I hope this helps. Have a great day.